So before we start any examples, let's talk about a couple of things relating to Newton's second law. So you might ask, how accurate is F equals ma, or Newton's second law in general? How accurate is it? Is it a law of nature in that it is exactly true, where if you write the sum of all forces, it's equal to mass times acceleration to how many ever decimal places that you care to write about? Or does it have a small error in it? Okay, so it's an equation. It's an equation about the universe, how the universe works in some sense. Is there an error in the term? Okay, what is the answer? So it is accurate, but to about, it turns out, 10 power minus 8, roughly, relative error. For objects moving at human, quote unquote, speeds. By which, what do I mean by human speeds? Speeds much less than speed of light. This symbol means much less than. When, of course, speeds get close to the speed of light, you get into issues relating to relativity at much higher speeds. Need to use a relativistic correction. Okay. So sort of due to Einstein. Okay, so it's super accurate, right? So it's like very small error, but it's not zero. The error is not zero. For objects moving at human speeds, by which I mean speeds of human walking, cars, planes, rocket ships, even the fastest rockets, are much slower than the speed of light. And for that, the error is about 10 to the minus 8, roughly speaking. Maybe 10 to the minus 9, 10 to the minus 10, or 10 to the minus 7. In any case, at much higher speeds, you need a relativistic correction, essentially theory of relativity from Einstein. Okay, so that's how accurate this is. It's super accurate, but it's not perfect. Okay. And then the second remark that I wanted to make is with respect to what reference frame, respect to what should we measure acceleration for, quote unquote, F equals ma. Okay, so we've already seen that there is no such thing as absolute acceleration. There is only relative acceleration. So the sum of all forces on an object, well, it is the sum of all forces. It's not really going to change depending on what frame of reference you're looking at. So with respect to what reference frame should we measure acceleration? And the answer is a little subtle. It's actually deeply philosophical, and it actually took a few hundred years to understand in some deep sense. Again, going back to relativity and so on. But A is measured with respect to what are called inertial reference frames. So it turns out there exists these reference frames or frames in the universe called an inertial reference frame, and A should be measured with respect to that for this equation to be true. Okay, what is an inertial reference frame? An examples of approximate inertial reference frame inertial frames. For our purposes, we will use Earth's surface. Center of the Earth, center of solar system, center, when we say center, we mean center of mass of solar system. Center of galaxy. So it turns out this is what we will use. So we will use this. It's only approximate. It's an approximate as an approximation. And this sequence, it turns out, Earth's surface, center of the Earth, center of mass of the solar system, center of mass of galaxy. This is a more accurate inertial reference frame than this versus this versus this. But because of the nature of our problems, we'll mostly consider Earth's surface. But if we want to consider planetary motion or motion of satellites around the Earth, we might consider center of the Earth. Or if you want more accuracy for satellite motion or motion of planets, we might use the center of mass of the solar system, and so on. So this way lies more accuracy. Okay, but using the Earth's surface as an inertial frame is a sufficient approximation for most of our purposes. Okay. These things we really only need to use if we are sort of doing dynamics at the interplanetary or a galactic scale, which of course you might want to do if you're like sending rocket ships to moon or something like that, right? Okay, so that's inertial frame, right? So like I said, it turns out Earth's surface is not an exact inertial frame, but it's a good approximation. Okay, so that's the takeaway. So those are two main things I want to discuss about Newton's laws. How accurate is it, and how should we measure acceleration? And then a sort of an aside, which is not really about Newton's laws, is acceleration due to gravity. What is its value? Okay, what is its value? So many of you might say 9.81 meters per second. And that's because that's the textbook answer. It's the standard value. But G changes quite a bit. Depends on position on Earth. Location on Earth. Okay. Example, I think if you look up Columbus, G, what is it equal to? Well, I think it's about 9.82. You can look it up. At other places, G could be 9.79. As low as, okay, so it could be as low as 9.79. Any questions about this? So it really depends on the location because the Earth is not a perfect sphere, and the ground underneath your feet might have different densities and so on at different points on the Earth, potentially, and those things can contribute to, and there's also altitude. Those things can contribute to different G's at different places. So you can check this. There's the so-called Wolfram site. Look up in Wolfram. Look up in Wolfram Alpha, which is a website. You can sort of look things up, among other things. Okay, so that's the end of this for this little video.